Now we're going to talk about expected value and variance of probability distributions. So just a brief recap of discrete versus continuous random variables, because you really need to understand random variables in order for us to move on to understanding expected value and variance. Then we're going to do a brief, hopefully brief, mean and variance review to just think about all the different kinds of mean and variance we've learned about so far. And then we're going to talk about the new versions of mean and variance of probability distributions. And then we're going to talk about three special situations: linear transformations of the random variable x and what happens to mean and variance, the sum of n independent values of x, and the sum or difference of independent values of x and y, so drawn from two different random variable pools. Okay, so there are discrete versus continuous random variables. So far we've been talking about random variables, right? Like x. And x could be, sum of two die that have been rolled. X could be the sum of two TV show times, right? X could be, it could just be something simple like the number of people in a room, right? It doesn't really matter what x is. X is whatever random variable, and then whatever that random variable is, you have the probability of those x's in your probability distribution. But so far what we've been looking at are discrete random variables. These are called discrete. They're numbers, right? Like when we have the sum of two die, they're numbers like 2, 12, right? But they're discrete. They're not continuous because having 1.7 as an expected value, that means that, let's say we had a distribution that looked at 1, 2, and 3, and 4. These are our x's, right? Having a 1.7, although there's meaning, it's like, on average, like we'll be somewhere around here for our distribution. You won't ever really get a 1.7. It's not possible to get that 1.7, right? So let's say we have the sum of two die. Let's say that ended up, let's say an expected value of uneven set of two die ended up being, 4.7. That's a perfectly fine expected value. But can you ever roll an actual sum of 4.7? No, that's impossible. And because of that, those are called discrete random variables. There are sort of bins that you have to fall in, and those are the only possible values for that random variable. Now, random variables like height are continuous because in something like average height or the sum of heights, right? It's not that I have particular values that you could have. You could have, all kinds of different values. Some might be less likely than others, but there are an infinite number of possibilities in between two sums, two discrete sums. So we're only going to be talking about discrete random variables and the probability distributions so far of discrete random variables. So far all the stuff we've learned about expected value and all that stuff, it only works for discrete random variables so far. Later on, we'll learn about how to deal with continuous random variables, and that's going to be exciting because it's going to open up a whole new world for us. All right. So given that, now we could do a brief review of mean and variance when we talk about samples, populations, and now we're adding on probability distributions. So with samples, remember the mean is going to be symbolized by x bar, while in a population, the mean is symbolized by mu. Here, the mean is symbolized by the expected value of x, or mu sub x, right? So first off, you know that the symbols are different. But the sample and population, what you end up having to do is summing up all the x's, right? I equals 1 to n, right? And then dividing by however many you have, however many, the number you have. In populations, what you end up doing is basically the same thing, except you just change the notation slightly so that it reflects that you are doing this for the entire population, not just your little subset sample. So here we have x sub I, just like before, but instead of I going from 1 to small n, we have from 1 to big N, and you divide by big N, the number of all the different people in your population. Now, at first glance, you might think, this, what we learned about expected value might look a little bit different to you, because we have the sum of all these different values, of all these different x's, times the probability of those x's, right? And you might think, oh, we're not like adding them up and dividing by n, right? But in fact, we are, because let's unpack what P of x is. If you think about the probability of x, think about like double-clicking on it, and we open it up. What's actually inside? Well, what's actually inside is the number of x, right? So the number of x, right? The number of times where you'll get x out of the total frequency, right? Total frequency, right? And so here, we are looking at something divided by the total frequency of however many it is, but we're also weighting it by the number of x. So before we had things like 1 out of 36. So there's 36 possible outcomes, right? And the number of times where you'll get, the roll 1, 1 is just 1 out of 36. So we could change that into a probability, or we could unpack it as the number of times you'll get x out of the total frequency, the total number of outcomes. So total number of outcomes. So that might be a little bit more transparent. So in that way, what we have is you're weighting x by how frequent it is, dividing by the total. And that is very similar to our notion of mean, right? Like you have all these x's, right? And you add them up, you divide by some total number of something, right? And in that way, we have that idea still present here. You just have to unpack it a little. Okay, now let's talk about variance. Now, before, what we wanted from variance was something like average distance away from the mean, right? Like we have all these points and we want to know sort of the average distance away from the mean. And we couldn't just look at deviations away from the mean, because when you have x minus x bar, sometimes that will be positive, sometimes that will be negative, so that ends up adding up to 0, right? So we would square everything, right? And here in sample, the variance we called s, right? S squared, actually. Here we would call this sigma squared, right? And let's start here. So the sigma squared, what we're going to do is just take all of the different squared deviations away from the mean, right? So take all these x's, and get all their squared deviations away from the mean, and then divide by n, however many of these x's we have, right? And it's the same I from 1 to big N, right? Now, when we looked at variance and, more importantly, standard deviation, which is going to be the square root of these things, what we wanted was the same idea. So the squared deviations, and this time we use x bar, right, squared. But now we need to do a little bit of a correction, right? And so we divide by n minus 1, right? And so in order to get standard deviation, we just square root both sides, and we get s equals the square root of x sub I minus x bar squared over n minus 1. All right. And you could also square root both sides here, right? And we get sigma equals the square root of the sum of squared deviations away from mu this time over n, right? All right, so that's sample population. But now let's talk about in probability distribution. Just like how here you see how mu is like population, because probability distribution, it's theoretical. So we use those Greek letters. Here we'll use sigma and square that for variance, but we'll also put that x there, right? And instead of expected value, we call this variance. So var x, right? So you could write it as var x or sigma sub x squared. All right, and if you really break this down, you could see the similarity, but once again, I'll put it in the probability form, where now you're summing x's, but here you just sum the x's. Now we're summing the squared deviations. So it's x minus, and imagine what you would put here. You wouldn't put mu or x bar, you would put its corresponding mean, which is mu sub x, right, squared times the probability of x. I'm like running out of space, but you could see that sort of, right? So you multiply all these together. And so it's the same thing. Here, if you break it apart, you could see sort of this piece and this piece, right? And this piece is very similar here. But now we're using probability to weight each x and then divide it by the total number of outcomes. But here, you could see, this part is very similar to these parts, right? And once again, you could break down P, the probability of x, to be number of outcomes that look like x over the total number of outcomes, right? So you could break it down. But here, I'm actually going to write the standard deviation form. All you do is square root both sides. So it's not just sigma, but sigma sub x will be equal to the square root of this whole thing. So sum of x minus mu sub x squared times p of x, right? Time I got it to fit, right? So, so you could see that there are some real close similarities, but there are some subtle differences now too. And I should say this is still for discrete, random variables. So this is in the case that x, big X, is a discrete variable. Okay, let's think about an example situation. We've seen this situation in the lesson previous. At the state fair, you can play Fish for Cash, a game of chance that costs $1 to play. You blindly fish out a card that has a dollar amount that you have won from a giant fish bowl. And here is the probability distribution of all these different winnings, potential winnings, and the probability of those winnings, right? So I've put those here. And before we looked at how to find the expected value. And now we know how to find the standard deviation of these winnings. We know the formula that we could use. And we could think about what the idea is. If expected value, if this is roughly the mean of the probability distribution, right? That's over time, over many, many cases, this will be the mean over the mean of winnings, right? Well, we could think about what variance of x means. That means, what is the spread around that mean? So if we had a large variance, it means that there's lots of spread around it. If we had a small variance, it's like, oh, it's very consistent around that mean, right? So you could think of this as the spread of the probability distribution, right? So the mean or center, right? So we're getting at these same concepts again, like shape, center, spread, right? So here we have center and spread, but now we're not just talking about any old distributions. We're talking specifically about probability distributions. Okay. So we could find the variance of this probability distribution if we wanted to. But I want to talk about some special cases. There are going to be some cases where you have a very similar setup to the ones that we've just discussed, where you know you need a probability distribution. But there are going to be some subtle changes. Okay? So one example is when you have some random variable, like winnings, right? But these winnings, or this random variable, is transformed linearly somehow. So remember, linear transformations are whenever you add a constant or subtract a constant, either way. Or if you multiply or divide by a constant, right? So those are both linear transformations, and doing some combination of those two. That it's still linear transformation. So an example situation might be something like this. You have that same Fish for Cash game, but maybe they have a special day where they have a promotion where whatever ticket you pick at random, you get triple the value for that day. What would be the expected value of that game, right? All the information you need is actually there. And so we're going to talk about how to find expected value and variance for this kind of situation. Another special case is if you have n independent values of x and they're summed together. So for instance, if you play that Fish for Cash game, but you buy 3 tickets, right? So you play it 3 times in a row, right? And so you pick 3 tickets at random and their values are summed, right? In that case, if you have n independent values, n of 3 independent events of this random variable, winnings, and they're summed together, right? And you want to know, man, what expected value should I have for this kind of situation, and what is the variance, right? So we're going to talk about that. And finally, the last special case we're going to talk about is when you have an independent value from x and another one from y, and then you either sum them together or subtract one from the other, so some kind of combination of that. So in this case, it might be something like there's 2 Fish for Cash booths, so 2 games that are similar, and you buy a ticket from one booth, and you buy a ticket from another booth, and you know the probability distributions of both x and y separately. What is the expected value of these summed together or subtracted from each other? And what is the variance, right? So these are the 3 different kinds of special cases that we are able to figure out just from having almost the same information we've had so far. We could just do a little bit of reasoning around these issues, and then we'll come to some shortcuts.